Namaskar, my name is Naresh Chandrapant and I am a professor in Department of Geology. Today we are going to talk about Pauling's rule. Well, we know that most of the minerals are crystalline substances, and to understand how they behave and what are their properties, we have to understand their fundamental structure. In understanding of their structure, it is important to constitute what constitute these minerals. There are two elements to this. One, the constituent particles, and second, how they are bound together. So, the bonds and the constituent particles are the important things. Now, in ionic bond and metallic bonded minerals, the nature of bond is such that they are bound in terms of their charges. For this purpose, we often consider them as spheres of different sizes depending upon or in proportion to their ionic radii. That becomes a fundamental thing, and we can start this by looking at the structure in terms of equal size spheres first, though naturally in minerals this is not the case. Now, if we have equal size spheres which constitute a crystalline substance, then there can be more than one type of arrangement which leads to a crystalline structure. So, if we look at one of the way, then it can be seen in this fashion, that we have spheres of equal sizes which are touching each other, and they represent the idea of what we call as closest packing. When we have spheres which are touching each other, we also have spaces in between where there are dimples or gaps. Depending upon how subsequent layers are stacked over one over the other, there can be more than one type of possible arrangement of closest packing in a simple case when all the spheres are of equal size. So, one of the situations, supposing we label this layer as A layer, the type of spaces which are there available are of two types. As you can see, they are more or less triangular spaces. So, some of the triangular spaces point downward and some of the triangular spaces have apices upward. So, we can consider them as the space designated as B and C. Now, we can have a situation where the second layer is placed over the vacancy position B, and if after the second layer the third layer is again placed over A, then it leads to an arrangement of the type where there is a repeat of AB layer subsequently, and it becomes an AB kind of arrangement. This is known as HCP or hexagonal closest packing. In the second instance, the third layer is placed over the dimple C, and After the third layer, the fourth layer is again repeated over layer A. So, that arrangement assumes a repeat of ABC, ABC, etc. And this kind of closest packing is called as CCP or cubic close packing. In both of these, the idea is that there is a central sphere which is in touch with 6 spheres around it, and then there are 3 spheres on top on one side and 3 on the lower side, which means that each sphere is in contact with 12 other spheres, and this is a 12-fold coordination. So, therefore, in both HCP and CCP, each sphere is in 12-fold coordination, but as we can understand, this will not be the case in most of the minerals, because most of the minerals have spheres of different sizes or the constituent particles representing different sizes. In case of certain metals, one can come very close to this kind of packing, like gold and silver alloys also, and if the sizes are equal, they will replace, and it can be a situation like this. In minerals, there are other cations also or other particles also. Now, in general, the anions are larger and the cations are smaller. So, the intervening spaces can be filled with those smaller cations, and it can lead to a compact and bound regular internal atomic arrangement structure, which is a crystal. So, Pauling looked at this idea of how the different cations and anions are bound together, and some rules or fundamental rules which govern this arrangement, and those are known as Pauling's rule. The first principle of Pauling's is known as the coordination principle. It states that a coordination polyhedron of anions is formed about each cation in such a way that the cation anion distance is determined by the radius sum and the coordination number of the cation by the radius ratio, and we will illustrate this soon. The simple case which we discussed earlier refers to 12 spheres touching the central sphere. Now, if there is a smaller cation like what we see here, that is the size or diameter of the cation is reduced, then the number of spheres touching around it will reduce. Now, the first case is where there are 8 spheres touching that, and we will examine this mathematically also. To touch the other surrounding spheres, we can look at it in terms of their respective radius ratios. The radius of the cation, that is the positive ion, is given as r x, and the radius, the diameter will become 2 r x, and that of the anion is r z, and since in this diagram, as you can see, there are 2 r z. So, this distance will become 2 r x plus 2 r z. Now, applying Pythagoras theorem, we can say that 2 r z plus 2 r x square is equal to 2 r z square plus 2 o 2 r z whole square. Now, 2 r z plus 2 r x is equal to 4 r z square plus 8 r z square to the power half, and if we see this, this leads to 2 r x is equal to 1.464, giving r x by r z as 0.732. Now, remember, this diagram is drawn when the sphere the larger sphere are touching the smaller sphere. So, it is the limiting condition. In the limiting condition, there will be 8 cations, 8 anions touching the cation when the Rx by Rz ratio is 0.732. For the Rx by Rz less than 0.732, the cation will be too small, or if we can consider that it will rattle at this side and the structure will have to change to a lower coordination. So, there the radius ratio of the cation and anion determines that how many fold coordination, that is the environment around a cation, will occur. By applying the same principle, we can arrive at 6-fold coordination, which is also known as octahedral coordination, also at 4-fold coordination and other lower coordination, and this implies that the radius of the cation will be comparatively lower. We can summarize this in this table, where the central column represents Cn or coordination number, which describes the number of anions around a cation. So, it starts from 12, 8, 6, 4, 3 and 2. It will be 12 coordination when the radius ratio is 1, which means that they are of equal size. The type of packing could be hexagonal or cubic closed packing, as we saw earlier. When it is the radius ratio is between 1 and 0.732, the limiting value, it will be 8-fold coordination and the type of packing is normally cubic packing. When it is between 0.732 to 0.414, it is an octahedral or 6-fold coordination and it is known as octahedral packing. When it is between 0.414 to 0.225, it is a 4-fold coordination, also called as tetrahedral coordination. Between 0.225 to 0.155, it is 3-fold coordination and is known as triangular coordination. And if the ratio of the radius between cation and anion is less than 0.155, then it is a 2-fold coordination and it is called as a linear type of coordination. The rule 2 is known as the electrostatic valence principle, and it states that in a stable crystal, the total strength of the valence bond that reach an anion from all the neighboring cations is equal to the charge of the anion. We can see its illustration beautifully in the structure of NaCl. So, it actually states that the valence is equal to charge on the ion divided by the coordination number. In case of NaCl, each positively charged sodium ion is surrounded by 6 chlorine ions with the singular negative charge. In the octahedral coordination, the octahedral coordination number is 6, the charge is 1. So, it works out to be 1 by 6. The strength of the negative charge which actually affects Na ion is 1 by 6. Hence, one positive charge is balanced by the 1/6 negative charge of 6 Cl ions. If we multiply 6 by 1 by 6, it works out to 1. Similarly, each chlorine ion is surrounded by 6 sodium ions in octahedral coordination, and again 1/6 of a positive charge from each sodium reaches the chlorine ion, and thus the Cl ions also uses 6 multiplied by 1 by 6 positive charge. However, this situation may not be similar in other structures. In CaF2 structure, each calcium twice positive ion is surrounded by 8 fluorine ions in 8-fold coordination. The EV reaching the calcium ion from each of the F ion is thus 1 by 4. Since there are 8 F ions, the total charge reaching the Ca ions is 8 multiplied by 1 by 4 or equal to 2, thus balancing the charge. In case of NaCl, where the charge is exactly balanced on both the anions and cations, the bonds are of equal strength and they are called as isodesmic bonds. In other cases where the bonds are different, that is the charge is not equally balanced by cations and anions, they are called as anisodesmic type of bonds. Let us say in case of carbonate structural groups like CO3, the C4 plus C ion are in triangular coordination with oxygen, and here EV works out to 4 by 3, that is Ca has a charge of 4 and coordination number of 3. Thus, 3 oxygen contribute 4 by 3 charge to the carbon ion, and the charge on the carbon ion is balanced, but each oxygen still has 2 by 3 of a charge that is unused, which leads to formation of bonds with other elements, and therefore, this is an example of anisodesmic type of bonds. The third rule concerns the sharing of polyhedral elements. The first part of this third rule says the existence of edges and particularly of faces common to two anions polyhedra in a coordinated structure decreases the stability of ionic structures. Now, this figure illustrates this very well. For tetrahedral coordination in this figure, if the distance between the cations in the polyhedrons that share corners is taken as 1, then sharing edges reduces the distance to 0.58. Thus, sharing of faces reduces the distance further to 0.38. The farthest distance between same charge particles leads to more stable structure. Reduction of this distance, say in case of sharing of edges to 0.58, leads to lesser stable structures, and further when the faces are shared it becomes 0.38 and the structure is less stable. Well, it is important also to recall the isodesmic and anisodesmic. There is also a category of bond described when the bond strength is nearly equal, that is called as mesodesmic. Coming back to the polyhedral element sharing, the effect is large for cations with high valences and small coordination number. The example is that of carbon with 4 positive charge in 3-fold coordination, and it is especially large when the radius ratio approaches the lower limit of stability which we described in the table for a particular polyhedron. When coordination polyhedra share corners, the cations are farthest apart, and this is followed by sharing of edges, and as we know that the repulsion of the cations is least when they are farthest apart. So, this leads to a relatively stabler structure. Now, this property is very significant when looking at the property of the minerals, because the property of the mineral is also dependent upon how stable the structure is. So, now we shift to the fourth rule of Pauling. The fourth rule of Pauling's also concerns the sharing of polyhedral elements, but in this, in a crystal containing different cations, those of high valence and small coordination number tend not to share polyhedral elements with each other. So, the sharing of the polyhedra is a function of the valence and the coordination number. Now, when we look at this in a figure, so an additional consideration follows from rule 2. Small highly charged cations form low coordination number. They form anionic groups when more than half of the charge is neutralized within the group itself. For example, the CO3 with charge of 2 minus, PO4 with a charge of 3 minus groups. Therefore, the oxygens can only bond with low valence cations in coordinations of polyhedra that are larger. This accounts for the lack of 2 ALO structures and tetrahedra bonding, though bridging oxygen in many silicates. The Al3 plus O oxygen, that is bond in tetrahedral coordination, has an EV of 3 by 4. If there was a bridging oxygen between two AlO4 tetrahedra, it would mean 2 into 3 by 4 is equal to 1.5 EV, and the oxygen minus 2 would not be satisfied. In this case, when sharing of edges occurs, the shared edges contracts to reduce the repulsive charge between the cations, and the cations are displaced from their particular polyhedral centers, which leads to a different symmetry also away from the shared edges, and this is the variation from rule 2 to the sharing of the polyhedral cations. Now we come to the last rule of Pauling's rule, and this is known as the rule of parsimony. And what it states is that in a crystal structure there are only a few cationic and anionic sites. If that is not so, and minerals being impure phases, it will be impossible to understand and categorize the crystal structure of minerals. We can see this and illustrate this with one example, that there are few cationic and anionic sites which are occupied by a large number of cations and anions. In that case, they can be considered as single or individual sites, not in terms of the different cations and anions. If we look at the formula of tremolite, it is like this. Now, in a typical amphibole structure, this refers to vacancy, and in a typical amphibole structure there are 4 octahedral sites which are termed as M1, M2, M3 and M4. There is a tetrahedral site which is mainly occupied by silicon, and the vacant site is called as A site, which is of a higher coordination number, which means that it is a larger site. Now, there are many elements which substitute in amphibole as this formula transforms to hornblende. So, there are 4 sites of octahedral coordination which are known as the M sites. Now, as the amphibole changes its composition, let us say during the green schist facies to amphibolite facies metamorphism, several substitutions takes place, and the elements which enter these structures can be clubbed as sodium, potassium, iron, magnesium, divalent, manganese and calcium, then trivalent iron, trivalent manganese, titanium and aluminium. So, we see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and more than 10 elements substitute for different elements, but the number of sites to which they substitute are limited. For example, the larger cations tend to go towards the A site, or which is marked here as the vacant site. The divalent cations and calcium tend to substitute in M4 site, and the smaller sites are substituted by these elements, Besides, aluminum also goes to the tetrahedral site silicon because of the ease and similarity of sizes and charge difference of only 1. So, therefore, we see that more than 10-11 elements are substituting, but they are being accommodated in relatively smaller number of sites. Therefore, the crystallographic sites in a structure for cations and anions are limited, though a large number of elements can substitute in those positions. The crystallographic sites remain as individual sites, the number of elements can be more. And this rule of parsimony actually helps in the way that we can understand a mineral and its changing composition much better. If this was not unrestrained in terms of the crystallographic sites, it would have caused lot of problems in categorizing, characterizing and understanding the crystal structures. Besides what we have learnt in Pauling's rule, there are few more things to notice. For example, if we look at uraninite structure where each uranium has 8 oxygen around it, and we look at CaF2 structure where each calcium has 8 fluorine around it, there is a similarity of structure, though there is no relation of the constituent particles in the two cases. This kind of similar structure is known as isostructuralism or isostructure. In another instance, there can be similarity of composition, but different structures. The aluminosilicates, kyanite, sillimanite, andalusite illustrate this very well. They are nearly pure phases, have similar chemical composition, but different structures. That is called as polymorphism. So, today we have learnt the Pauling's rule, which describe and define the relationship of the radius ratios of cations and anions, their structural arrangement, the limitations of those structural arrangements and the requirement of these in understanding the crystal structure of minerals. Thank you.